So anyway, some of these things are addressed with semantic probabilistic layers, but there's things that LTN does, such as first order logic, that to date aren't done by SPL. So this will be an interesting approach though. So they talk about in the paper, they say, well, we're going to call sort of your general sigmoid function outer layer a fully independent layer, because basically it's assuming that the labels are provided independently. So they write out the product. And so, well, why not just replace that layer with something like this, where you're predicting labels Y conditioned on F, which is the neural network, X is the input, and it's going to be dependent on function Q, which is parameterized with data, which is learned from data. And Q is learning correlations between the labels from the data. Okay, so Q is trained as part of the process. And then you have CK, which are hard constraints that get embedded into the network as well. And so you have these two functions, and you have a normalization constant. And of course, looking at this, it looks quite terrible because you're summing over all possible combinations of the output labels. So if you have a whole bunch of ground atoms representing output labels, this is going to be intractable, which is a common thing, right? If you look online at Jerry's lecture on Markov logic networks, like they run into this problem. They overcome it basically by sampling, and it still results in scalability issues. But here, they overcome it by restricting what those functions look like. And so they show at the beginning of the paper, and I kind of like this stuff, maybe it's just me. They have some desiderata about things, well, the layer should have all of these things, okay? So, but of course, first order logic's not listed on there, for example, but never mind that. But they do make a good case here, like this is actually, really probabilistic, okay? So it abides by the probability axiom, so it's a true probabilistic approach. It's expressive in terms of what it can encode. It assures consistency, which this is a big plus. And then they make some cases about, modularity. It also is, they make a good case for it being efficient, but there's limits to that. So the main idea are those two functions, the C and the Q function, are created using what are called probabilistic circuits, which are essentially just these sum product networks. It's a very straightforward thing. And then these sum product networks, they can be weighted, and you can build them up in a modular way. And sort of the basic idea here is the Q function is going to be a probabilistic circuit where the parameters, these weights on the sums, they're going to come from the neural network. And the neural network is being used to learn the parameters of the probabilistic circuit that gives the output. The other function, the CK function, that comes from constraints, you have these logical constraints, and they're compiled into a probabilistic circuit. So there's two big properties they talk about, smoothness and decomposability. With smoothness, every sum unit depends on the same variables. With decomposability, every product depends on disjoint variables. Now, right away, this should kind of start to look maybe like something we've all seen before, like a Bayesian network maybe. And these properties, you can really think of allowing sort of a local independence within the structure, because if you have smoothness, every sum depends on the same variables. That means you can think about all the inputs to a sum being mutually exclusive, and if you have a bunch of mutually exclusive thing with probabilities, and you sum them together, getting the disjunction of those different events. Likewise, the product depends on disjoint variables. If you have independence there, you can then take the product of those probabilities and you get a legitimate conjunction because you have this independence. So these properties also give rise to this notion of compatibility that allows these probabilistic circuits to be combined in a modular manner. And that's kind of that plays a big role in allowing you to have both the Q and the C probabilistic circuit together in the same neural architecture. So a probabilistic circuit can model a probability distribution over subsets of labels, and they parameterize it based on this function G, and G is applied to the last layer of the neural network. So remember, we're getting rid of the output layer, so that stuff has to go somewhere. So it goes to this function G. So what is G? Well, G is just, what they just used is a simple multi-layer perceptron, and the output layer of that, the parameters for the sum is done with the softmax layer, and the parameters used for the product are sigmoid. And this makes a lot of sense, right? Because it ensures that, you know, you have this kind of mutual exclusivity and this independence, you know, property there. Okay, so we got function Q. Well, what about C? Well, given a logical constraint, it can be compiled in an ordered binary decision diagram. Now, this is something that's common in the verification community, where you got something like an MDP or a Kripke structure representing a process, and you have a formula, usually in like a temporal logic, like LTL or CTL. And you know, one of the big results in that line of work over the years was, hey, you can take the CTL formula, you can compile it into something like an OBDD, and then that will allow it to play nice with your Kripke structure. Well, previous work prior to this paper shows that the OBDD can be translated into a probabilistic circuit. Now, the worst case is the size of the OBDD could be exponential in size of the CNF representation of the formula. But the thing is that these methodologies have been around for a long time and have gotten very mature. It's been observed that when you actually do this process, it ends up being much smaller. And so they're taking advantage of these practical implementations. Now, one thing to keep in mind here, though, is because this technique that came out of the work of the verification community, the verification community is really concerned with checking a series of what they call specifications, which are their logical formulas. And if the system abides by that, that's not a logic program. It's just like a bunch of logical sentences that we don't want this behavior to ever occur. And so, my question is, would this scale to do something like what ABL is trying to do, where you actually have a logic program, or what some of that work toward the end of the ABL lecture, where they wanted to, generate a really big logic program out of a knowledge graph? That's where I would start to be doubtful. And I'd also be doubtful is if you wanted to extend this to the first order logic case, you essentially have to be grounding out your first order logic statement into a bunch of formulas. And that would also, we'd start to see increased size and things here. Now, I'm not saying that it wouldn't work or it would necessarily be exponential in size, but it hasn't been shown that this could be done yet. And that could be where the limits of scalability occur. So putting this all together, then they provide a strong theoretical result where this allows for efficient inference, where it's in the size of the Q circuit multiplied by the size of the C circuit is, the complexity of it. So if you're looking at only, Q is you get to pick how big that is based on how many correlations you want to capture. C comes from your logical formula. And so if you only have a small number of constraints and it doesn't blow up when you do the conversion, this actually ends up being pretty fast. So experiments, so they look at this Warcraft pathfinding experiment where it has to find a path from the game board that has to also be a legitimate path. So finding something like this, which is produced by a sigmoid output layer, doesn't make any sense because you have big gaps in the path. It's not a valid path. Even with semantic loss, they found that it would often not return a valid path. But here, where they're assured of consistency, it has to return a valid path in the solution. And so when you see the results up top, this one trivially gets 100% on consistency. And that's just because it has to. It's just designed that way. It can't violate those constraints. The other thing interesting too, and this comes up in this paper a lot, is this exact match versus Hamming distance. And the Hamming distance basically is giving sort of credit for partial solutions. But what could happen there is you could have all of these paths, or a huge number of the paths in the test set could be off by a little bit, and it could cause this Hamming distance number to be inflated. So even though they don't do as good on that, for exact match they do better, and they're giving actual paths 100% of the time. They did a similar comparison to the HMCNN that I mentioned at the beginning of the lecture, and this primarily has been used on things like medical imagery. Both approaches can guarantee consistency, so they both scored 100% on that. The place where SPL starts to shine is in terms of exact match. It outperforms HMCNN, even though that does better on the Hamming score. But even in this case, SPL is not that far off, usually just 1% or 2% behind on that. And HMCNN at the time of the writing of this paper was state of the art for these tests. So again, I mean, this is really cool because they have a tractable framework that is really probabilistic. Constraints are strictly enforced, so that's really great, especially for tasks dealing with robotics and safety and stuff like that. And also not really featured in the experiments, but the output layer is also learning correlations among the output classes at the same time. I don't know, how they could have measured that and shown that empirically as well. But that's kind of an interesting thing. And the whole thing is quite elegant. Like it's very strong theory, implementation reflects the theory, very crisply. And so I think that's great too. It's only propositional though. And no notion of multi-step inference. And we don't know what happens if you go to like really big logical statements. The other thing is the identified correlations by Q. They're likely not interpretable, which is probably part of the reason they didn't talk about that in the experiments. And the reason for that is you got kind of a mess of parameters going into that Q function that dictates how that that PDF works, and it probably is not anything you can make sense of, I would guess. The other thing too is there's kind of this implicit closed world assumption that goes throughout the whole thing. And honestly, most of the approaches that we're talking about actually have this. LTN has it as well, where if it's not true, it's false. And so that's definitely present here too. All right, so we do have a little bit of time. I'll quickly go through STLNet. So I'm not gonna talk about temporal logic, in great detail, but just know that the temporal logic formula it's going to be, you have an output that is a sequence of things, and we want to check if that sequence satisfies the temporal logic form. So the additional operators allow you to judge, something at time 1 versus time 3, if those go together and so forth. So you have these n times, you have sequences of m variables over m time steps. And then they have prefixes and suffixes, where the prefix is basically your input sample, and you want your model to generate like some kind of output. So think transformers and recurrent neural nets. And so, yeah, so this is the output goes from positions, goes from position I+1 to n for each sample. And f is your neural function that takes in the first I positions of the sequence as input. So we have some properties that we want to satisfy. These are our temporal formulas, temporal logic formulas, and STL is what they use. And the idea is you want to find the parameters for the model that minimizes loss such that the output of the model satisfies the constraints. And yeah, they use D as distance function, part of the loss, L2. So this is just an example of some of the different types of temporal constraints. They actually have logic here. But these are all things like, there should be at least one patrol car around the school every day. So if there's like a scheduling problem, and these safety issues, there will be certain requirements you have to do, have minimum things. In business world, you have things like SLAs that companies have to abide by. So if you're doing things in an automated way, you need to make sure those are adhered to. So they have the student network is the basic neural network. That's the thing that is predicting the output sequence. What they call a teacher network is actually more of an algorithm. What it does here is it's taking the output of the neural network and it is effectively correcting. In some ways, that's similar to the idea behind ABL. But it's not doing it with abduction. It's more of a deductive process. Then they're using a special loss function applied to the student network that is a little bit different than what we've seen in the past, where the loss function considers accuracy, but it also considers how close the output is to the result of the teacher network. And you iterate between the last two steps until the results of both the student and the teacher look the same or close to each other. And so this is that loss function I tell you about. You have hyperparameter B. It's a number between 0 and 1. This is your standard loss. And this is a comparison between the teacher results and the student. That is weighted with 1 minus beta. So what's interesting is you get two results. So you get the student result, which is going to more accurately represent the data. But you'll get the teacher result, which is guaranteed to meet all the constraints. And I think that's what's, that's one of the main reasons I wanted to talk about this one, because, we've seen several approaches now where sometimes you have kind of a fuzzy version of consistency, and sometimes you have very strict. Well, this approach gives you both, and you can just pick which one based on your needs. And so here's the main idea. Again, they show an R and N, takes the input. Then the teacher network is going through, is doing this thing called a trace generator that is taking in as input the formulas and using that to replace parts of the output of the student network. And that's how it completes the loop. Adjusting the result. So we'll talk a bit about how they go through this process. So the first idea is converting the specification to disjunctive normal form. Now this is where we have some of the same questions that I had about SPL. Because in the experiments here, they generally looked at constraints that are where the logical formula is very small. Well, converting to DNF, you could potentially have an exponential log. And so there remains an open question of this approach can actually scale. So the idea here is that if you, by converting it into this DNF form, you essentially have, a sort of a state or a world associated with each time point. And based on that, you can now do a direct comparison with the output of the neural network, and you could just easily replace the minimal number of symbols to make it correct. So then they talk about how the formulas have an associated DNF representation, and they provide an algorithm to do so. And so results on generated data, they looked at generated sequences, both LSTM and transformer. And they look at, this is the P and Q, where Q is the teacher and P is the student. And so you see satisfaction rate, is not at 100%. But in general, you're looking at higher satisfaction rates with the student network than with the baseline approach that doesn't do anything to address consistency. Likewise, satisfaction rate here is, at 100%, because again, they're guaranteed that result with the teacher network. Another shortcoming of this paper is beyond simulated study, results are a little limited. They did have one data set on air quality prediction, and they look at, results here for, the prediction length, satisfaction rate, and so on. But again, it's, I think STLNet probably would need a lot more verification empirically, and a lot more examination of things like, what is the role of the hyperparameter? How sensitive are these results to the hyperparameter beta that does the trade-off between consistency and accuracy? Also, how does this scale in practice in terms of larger logical formula? And those remain open questions.
So reasoning shortcuts. So this was something I came across in preparing one of the other lectures, and it's super interesting. So, okay, so we have, everyone I think is sort of familiar with examples like machine learning fail when, bunch of wolves, a bunch of dogs, like the dog in the snow, and the branches also. And it's obvious, you see an animal or whatever, or in a bunch of creatures with snow, and the thing that, could be a dog or a wolf, continue to say it's a wolf because all your training data is wolf in the snow. And of course, there's like all these things like aliens maps, and to get idea for what evidence animal is a husky, animal is being blue, and aliens map is kind of showing the same thing. Sometimes these techniques, show you the difference. Sometimes you get results like this, and there's really no assurances. What happens, if it's going to actually work. So, okay, so we see all these kind of normal complaints about machine learning, and of course, AI to the rescue, right? But, good problem is combining the best of both worlds, gradient learning plus logical structure. We got all these great methods, right? Well, it turns out that you can still have some serious mistakes. So let's just review a quick setup, and I'm going to use this setup in this lecture. You'll see it's very similar to a bunch of the previous lectures. We have some logical knowledge base, K, and we say that we have some function, K, is a measure of the inconsistency in the knowledge base. And then we have training data, X is our vectors, Y's our ground truth labels, and P is our data set of the XY pairs, that's the training data. And we have a set of primitives or concepts, P1 through R, and they are in the language of K. And we have some perceptual model that maps features to concepts. So P beta X returns a concept or set of concepts for sample X. And so using gradient descent, we want to minimize the following. The knowledge base, the ground truth, dealing with the results of the perceptual model, right? Because if some of the concepts in the perceptual model combined with K, for each sample, it should give you the label of sample I and not something wrong. But that's all stuff you all should be sort of familiar with. Right? Okay, here's the thing. One of the things about gradient descent is one of the reasons that a lot of people think it works as well as it does with neural networks is that through over-parameterization, there's actually a whole bunch of solutions that it can reach that will be optimal in terms of that model. And so you don't have a unique solution. So what if we have perceptual failures that make it easier for the logic to work? So we confuse two different things. If we confuse all dogs with wolves, for example, and all we care about is something at a higher level concept, maybe the system can get away with that. So what you have is you have functioning logic, minimize loss, but the reasoning behind it is all screwed up because I defined everything wrong. So it's like raising a little kid and telling them that everything that's green is purple and letting them believe that their whole life. So this misinterpretation of symbols is called unintended semantics. And leads to what are called reasoning shortcuts. So it's finding this sort of shortcut through the optimization process. It's like, aha, that's optimizing the loss function, but that's the right semantics. I'm just going to go with that. It's a shortcut. So quoting right from the paper, simply predicting multiple concepts jointly from a single neural network is sufficient to enable reasoning shortcuts intuitively. Because the network has access to all properties of objects, it can automatically exploit correlation to satisfy the knowledge. That's kind of the key thing. It's going to exploit these correlations to satisfy the rest of the knowledge base. And that's what gives rise to these unintended semantics. So how to think about this? The authors of this paper came up with this sort of theoretical model of how things are generated. So let's say we have two factors. We have some ground truth, what the objects really are, and some stylistic variation. So of course, this could be variations due to the sensor use, or if it's handwriting, how the digits are written, or whatever. And both the ground truth and style items contribute to actually perceived. Yeah. However, only the ground truth is associated with the actual label. And of course, this is assuming we're going to generally make the assumption that there's no issues with the logic program. Okay. So going from X to C, this is where the perceptual part of the neural symbolic system comes into play. And the neural symbolic system then uses C to deduce Y to Z. So the goal of such a system is to have a correct understanding of the underlying semantics and allow it to infer the target label. So essentially, we have this perceptual model. We want it to be equivalent to be providing the equivalent probability distribution to the ground truth labels of concepts. So G is the ground truth of the concept, both conditioned on X. That would be the goal. So what happens with the reasoning shortcut is you get some P theta that is not equivalent to this P star. So, okay, so we have, if you look at your loss function, you have your loss function, you're looking to find the parameters that over the data points are minimizing or maximizing that function, depending on how it's framed, based on both the data and the knowledge base. And you have a reasoning shortcut when you do that, and the P theta is not the same as P star. So the strategy to reduce these is first, can we just see if we can somehow count the reasoning shortcuts? So we know there's got to be at least one valid path. If there's a valid solution to the problem, P theta equals P star, and you're good to go. Okay, but of course, finding a unique solution is going to be very difficult. So what we want to do is analyze a bound on how many of those are there. We can then develop strategies to just reduce the number and employ those strategies as part of our approach. And then here we'll show the author's results from empirical evaluation. So they introduce this notion of a function alpha, where they say, okay, we're going to say for some deterministic model P theta, there is an associated alpha function where you're mapping that maps the ground truth concepts to C. Okay. Now in P star, this is alpha of some C is going to equal C. It's going to be different than anything else. And so here, we're just looking at this alpha function and counting how many of them can exist. So first, as they say, okay, we're going to have a theorem to put a bound on the number of the strategies. Or this is actually a full count because you actually have alpha. And you're just going to say that, well, I have a little walkthrough here. So they introduce this function beta of k. It maps concepts to target labels based on k. And then you have this composition bk composed with alpha, and that maps predicted concepts to the target labels based on k. And so essentially all we care about here, both these functions are returning the ground truth concepts, the Y. This is mapping the concept to there, and this is mapping the predicted concept to the final. When they're equivalent, we're going to include them in our count. Regardless of the concepts are the same. The concepts are the same, that means you have a correct solution. If they're different, is the reason for it. And the general idea is you're going to only have one good solution with semantics of I. And you have a whole bunch of these other functions where you have a different alpha that's incorrect. Now, one thing to note here is this may sound really difficult because you only have one alpha that's going to be right. But this doesn't mean for the result of gradient descent that there's only one solution you could have, because there could be multiple assignments of weights that can lead to the ground truth solution. Also, this particular result is for the deterministic case, which is also a simplification. They do include another theorem that builds on the non-deterministic case based off of this. But I'm just going to keep talking about the deterministic case to keep it simple. The results, the relationship between direct, so it's not that big of a deal. You reduce one, you reduce the other. Okay, so the key here is when you look at this quantity, it's related to the number of satisfying assignments of what's being counted in here. This is a conjunction over all these potential ground truths. Okay, so if we can reduce the satisfying assignments, we'll reduce the number of reasoning shortcuts associated with it. Now, one way you could do this is you could make this conjunction longer. For any logical conjunction, I say, hey, what are the number of things that satisfy A and B? Well, what if that's going to be much greater than if I say it satisfies A, B, C, D, E, and F. Or you could think of it as almost like a database, right? Give me all students in CSE 598. Give me all students in CSE 598 that are in their second year of their master's program. All students in CSE 598, second year of their master's program who are applying for a job in Silicon Valley. It gets less and less the more constraints you put on. We're taking the same strategy here. Associated with that is also the size of the knowledge base. That also constrains the problem in a little different way. You have larger knowledge base, you have more constraints there. You also reduce the reason. Okay, so the first is with multitask work. And the idea is that if you have a set of concepts and they're used for multiple tasks, then that effectively functions as additional constraints. And you see what happens here. You now have the conjunction on the inside of the first one that is over T tasks. So you could think of it as, so if I tell you, give me all pairs of real numbers, let's say all pairs of natural numbers between 1 and 100 that sum to 20. But then I say, okay, give me all natural numbers between 1 and 100 that sum to 20, and numbers such that their sum or such that their difference is 5. Okay, so right away, because you have the extra task on, you reduce this. You could also think of it, going back to the driving example, maybe we have a task dealing with safety, maybe you have a different task dealing with recognizing it as destination. Two different things, but they may have to have a lot of the same underlying concepts, such as the lines on the road, the traffic signs, where the parking spaces are, and so on. Those concepts would maybe deal both with the two different tasks. Now, of course, the downside to this is you might not have an additional task. So that would kind of, not be good. And also, identifying additional tasks doing that extra work may also end up, leading to computational issues as well. So here's some results on doing this. So they look at evidence problems. They look at learning, add and multiply digits, and then so they evaluated this with 3 different neural symbolic frameworks: Problogue, Semantic block, which is a competitor to SPL in the other day, and then of course logic networks. And you see what happens how these perform individually. Y is ground truth, C are the concept. So if you look at the ground truth, the big semantic block, on the ground truth, it's doing really well. But we see clear reasoning shortcuts. It is catastrophic failure from the addition problem. And it's only getting 76%, which sounds okay, but that's down from 100% on the ground truth. But when you have both maps together, it's doing quite well. And we see this across the board in this example. So that's, I think, a nice intuition that is validated here. So we can also see here, looking at confusion matrix, what happens when you have add only and multiplication only. You see, almost all the time, you don't have any diagonal lines. So you see it's quickly becoming confused. But when they're combined together, everything's looking all right. 2 different mathematical operations, and it allows us to sort out some of the details between the digits. And again, remember here, this problem was not supervised on the digits, only supervised on the bytes. The digits are the concepts. Okay, so next, speaking of supervision of the concepts, why not just supervise the concept? We have the data. So this, of course, has, it's obviously going to help things. It's essentially adding an additional conjunction. And this idea already, we've seen it in some of the other papers we looked at. We've seen AVL does this to bootstrap things. They use some initial supervision of the primitive. And LPM does this all the time. The downside is you might not always have that data. And here's the ground truth concepts. So one thing that could be considered is maybe having some unsupervised approach to sort of separate out the concepts. So I want to learn concepts that are sort of far away from each other in the teacher space. And this becomes helpful when the unsupervised model is not separating things based on stylistic properties. So if we had an unsupervised, you're doing this with eminence, and the unsupervised model was separating out people who write, very block letters cursive, that's not going to do you any good. Whereas separating out by digits, and if you remember from earlier in the term the Satnut paper, Torpan is essentially doing their unsupervised step for Satnut. Another approach is just heuristic approach. So the authors are not able to prove any kind of reduction in the number of reasonable shortcuts using entropy. They do note it may not be appropriate in certain domains because you may not want to, minimize necessarily the diversity of the result in all cases. However, in the problems they look at, it does have an impact. So here we have H is entropy, C is supervision on concept, and R is reconstruction, which is unsupervised. Unsupervised control. So again, here we're seeing that generally steady increase the more you pile on together in more stable on the concept. So that's also kind of the neat thing about it. These things are all reducing the reasoning shortcuts in different ways. So here's just an example of, again, the confusion matrix, what happens and this even odd thing. And you see with deep prop log and LPM when you're running all the different methods together, they go from being sort of very poor confusion matrix on the concept to being diagonal lines. It's interesting to see that these results aren't uniform across all methods. Another idea is what they call architecture-based, where you can factorize the perceptual function. And this also causes alpha to factorize in third, which reduces the number of mappings. And so they also show here, highly effective in reducing your reasoning shortcuts, providing really good results compared to the baseline, effectively eliminating all reasoning shortcuts. However, in order to factorize it, you have to have some knowledge about the underlying problem in order to do so. And here again is the confusion matrix. This one got perfect results, no surprise there. And it got those results across all three neuro-symbolic methods. So, machine learning can provide correct answers for the wrong reason, but neuro-symbolic methods can too. I think that's kind of a big important lesson. But, mitigation, either making some assumption, adding more constraints, adding somewhat supervision to part of the problem, can go a long way in reducing reasoning shortcuts. And what's nice about this paper is, now we're getting to the point in neurosymbolic reasoning where people can start to look at, hey, what are some common approaches